Yes. We'll talk about that after. All right, guys, listen up. So let's think back for just a second about rate and rate constants. So we solved for rate constants, K, and that was basically just a measure of how fast the reaction was going to go. Because the rate told us how quickly we're going to do a reaction. So today, after last time we wrote rate laws and solved for rate constants, today we're going to look at equilibrium expressions and equilibrium constants. Okay? So just to make things easy on you, rate constant and rate constant and equilibrium constant are both K. Okay? So K represents both of them, but they mean completely different things. Okay? So rate constant told me how quickly a reaction happens. The equilibrium constant tells me how much product I make. Okay? Do I make mostly products, or do I make very little products? So we know for this to apply for an equilibrium constant, we have to have a reversible reaction, correct? If we don't have a reversible reaction, we're going to make all products and be done. But with equilibrium, we have a forward and a reverse reaction at equal rates, so they're both moving at equal paces, so we get a steady amount of reactants and products. So how did we solve for rate constant K? What did I have to solve for the rate constant? Well, what do we call all that stuff that I gave you? Where did it come from? But where did that come from before that? Experiment. You had to have experimental data to find the rate constant, right? You had to have that data in the table they either gave you or you found in lab. For equilibrium constant, you do not have to have that, okay? But for rate constants, was it super imperative that you balance the reaction? Not really. You should have, but it wasn't really important. But for equilibrium constants, it will be very important that you balance the reaction. So let's look at this kind of generic reaction. A plus B gives me C plus D. So the big letters are just molecules. The small letters are coefficients. Okay. So if I have this reversible reaction at equilibrium, I can calculate K. So I can say K equals, so to calculate K, I need, let's just write it out, then we'll talk about what it means. So I'll do bracket C, that's bracket capital C. So what does bracket capital C mean? Concentration of C raised to the baby C power. So the baby C, what do I call that? A coefficient. So if it's 1, we just leave it off, times concentration of big D raised to the small d power. There's no addition. Okay, we aren't adding anything together. It's all multiplied. Divided by concentration of big A raised to little a power times concentration of big B raised to little b power. So it's concentration of products divided by concentration of reactants, all raised to their coefficient. So what units, or what does the bracket mean again? It refers to concentration. So we assume what units? Molarity, so molar. So if I have capital M times capital M divided by capital M divided by capital M, what units do I end up with? They all cancel, right? So K for equilibrium has no units. Okay? So rate K had units. We just didn't worry about them because it was complicated. Equilibrium K has no units. So there's a difference there. It's unitless. So let's look at an example of why we even need to calculate this. So this is what we would call the equilibrium expression. Just K equals the concentrations products over reactants. Let's think about a situation. Let's rewrite two different scenarios. So scenario A, scenario B. So I can have A plus B makes C plus D. Adjust my camera. Then I could have A plus B makes C plus D. Okay, so for both scenarios, I want to mix 1 molar A and 1 molar B. Okay? So I can't plug those two numbers in and solve for an equilibrium constant, because if I just dump two things together initially, do I have an equilibrium process? No, I have to have a reversible reaction with products and reactants where the rates are equal. Initially, what's my concentration of C and D going to be at the very beginning? 0. Okay, we have no reaction yet. So now let's say scenario A, I give it while to equal out. Eventually, the forward rate equals the reverse rate, and then we are at equilibrium. Then can I calculate the equilibrium constant? Yeah. So let's just say my final concentration for A is 0.1 molar, for B is 0.1 molar, for C is 0.9 molar, and for D is 0.9 molar. So did I do a pretty good job? Or did the reaction do pretty well there? Yeah. Okay. So I used up most of the reactant to make products, right? So is that a fairly efficient reaction that I did there? Yeah. So now can I calculate the value for K based on that given data? Yeah. So go ahead and do that. So we'll assume all the coefficients are 1. Okay, so we'll assume it's already balanced. So go ahead and type that in. So 0.9 times 0.9 divided by 0.1 times 0.1. What'd you get? 81? Type it in again. Should we get 81? Okay. Units? None. Okay. So just K equals 81. That means nothing at the moment. It will in a minute. Okay, so let's stop. Let's go to scenario B. Let's say scenario B, I do the same reaction. I end up with 0.9 molar A, 0.9 molar B, 0.1 molar C, 0.1 molar D. So was the second scenario as efficient as the first? No, I made a lot less product, right? So now can you calculate the K value for scenario B? So you should get 0.0, then a 1, 2, 3, 4, 5, right? So 0.012. So which reaction was more efficient? A. Which one produced significantly more product? A. What can I say about the rate constant for A versus B? It is significantly higher. So what generalization could I make now about rate constants? The higher they are, nothing to do with speed, the higher the concentration of products relative to reactants. So I can make the statement, if K is greater than 1, products are favored. What does that mean, products are favored? Equilibrium shifted what direction? Towards products or reactants? Products. So we're going to get more product relative to the reactants. So if K is less than 1, reactants are favored. So if K is equal to 1, numerator equals denominator, so it's equal there. So can I use the value of K to make a generalization about how efficient the reaction is? Yeah. If I'm trying to make a lot of product, what kind of K do I want? High as possible, right? The bigger the better, the more product I make. So now let's think about a Le Chatelier's problem, or question, Le Chatelier's principal question. So if I have a situation that shifts equilibrium to the right, if equilibrium shifts to the right, do I make more product or more reactants? More product. Okay? So if I make more product, would that correspond to a larger K or a smaller K? Larger K. So I can now ask a Le Chatelier's principle question: if I do this to the reaction, will K increase or decrease? Okay, so shift to the right, K gets bigger. Shift to the left, K gets smaller. So just like with rate constants, these are constants, but only for a certain situation. Okay, you have to have closed system, so nothing coming in, nothing going out. Constant temperature, constant volume. So if you change anything about a reaction, the K will change. Okay, so changing temperature changes K. So you can look up values for K for a certain reaction, but they're going to be at 25 degrees Celsius. If that changes, that no longer applies. Okay. Questions about that? Good. So a couple of notes here. Brackets mean concentration. An important one here. Solids and liquids, solids and liquids, let's try that again, are excluded from a rate expression. So we do not include solids nor liquids. They are not significant contributors to the equilibrium process. So if I don't include solids and liquids, what do I include? Gases, aqueous. Okay. So if B were a solid right here, that would be the expression I would just leave it off. Okay. If A and B were both solids, that would be the expression. Just leave them both off. Okay, so you only include gases and aqueous things. Okay. Then you see you have K, KSP, KB, KA, you have KAQ. There's a lot of different flavors of Ks. And you'll talk about them more next year. We'll talk about a few of them next chapter. Just be aware for now, if you see K with a subscript after it, the subscript just tells you what type of reaction you're looking at. Okay, so don't worry so much about it for now. We talk about acids and bases. We'll look at Ka for acids and Kb for bases. But we'll look at that later. So for now, let's just look at a couple of examples of writing equilibrium expressions. So the first one, we don't have to have an actual chemical reaction. Can we have an equilibrium that exists between a phase change? Yeah. So can I write an equilibrium expression for that? Yeah. Do I include gases? Yes. Do I include liquids? No. So I would just have K equals concentration of H2O, gas, and that's it. Okay. I'll leave off the liquid. There is no denominator. Okay. So products divided by reactants, reactants get left off, so it's just the numerator. That's easy, right? So we'll practice writing these, then we'll kind of look at what they mean and why we use them. So for this one, KSP stands for solubility product constant. They define it as solubility equilibrium. So if you look at PbI2, if you look on the back of that yellow table or the orange table that I gave you, you'll see that it's not soluble. Okay, so PbI2 is insoluble. What does this reaction show PbI2 doing? Dissolving, right? Should it be able to? No. So the solubility rules are kind of a broad generalization. Everything dissolves a little. Okay? To say it's insoluble means that not a single atom is going to dissolve. That's not true. A very, very small amount dissolves. If a very small amount dissolves, we don't care about that small amount. Okay? But this reaction does happen. Okay? So if I get a very small amount of products, would I expect the K value for this reaction to be very high or very low? Very low. And you can Google it. Okay? So these are constants that are known. And then if we write the expression for KSP, I have the concentration of Pb plus 2 AQ times the concentration of I minus AQ squared. So then if I know the value of KSP, could I potentially solve for the concentration of lead to figure out how much I actually have dissolved? Yeah, so that's a useful application of this. If we know KSP from a table, then I could solve for the other concentrations. Okay.
So we're assuming the H2O is liquid?
Yes. So we leave H2O off because it's a liquid. We leave PBI2 off because it's a solid. Okay. So go ahead and do number 3. Write the equilibrium expression for number 3. So notice all these are balanced for you. If they weren't, you can't get these right if you don't balance it yourself. Then you go ahead and try the last one. The last one we'll spend a lot of time on next chapter. For now, just know that Ka corresponds to acids ionizing. So it's the ionization constant for an acid. So nothing changes as far as writing K versus Ka. We'll spend a lot of time discussing Ka in a few weeks. Yeah.
Does the charge have anything to do with it?
No, we just write the charge so we know it's there. We don't like raise the exponent or anything. Only the exponents are coefficients. Okay. Questions about that? Not difficult, right? So if we look over to the back, there's a couple for you to practice. And then there are some problems with numbers. Okay? So if I give you the concentrations of several of the reactants and products, can you plug that into the equilibrium expression and solve for K? Yeah. So go ahead and do these 4, and then do these 2 examples. And if you're on recording, you can pause it and check your answers there.